Okay, so lesson 10 is talking about power functions. And what we're mostly doing is we're looking at these and we're going to define some things about them. So the first thing that we're going to talk about is the domain. Okay, so a domain is all of the x values that are possible. So you may be thinking, well, what does that mean? So, which is the question with this, is just figuring out, making sure you understand what can possibly limit your domain. Okay, so first of all, if you have just like a linear function, the domain is not limited at all. Any x value that you choose will have a value in this function. Now what happens is, so pretty much any continuous function will have all x values. Okay, but what happens is there's other functions. One is if there was a whole. So if there is a denominator that has a 0, that would create an asymptote. Or if there's a denominator factor that's in the numerator as well, that would create that whole. Another situation would be a radical. So for instance, the graph of y equals the square root of x looks like this because you cannot put a negative value under a radical and get a real number. So this would have a limited domain from 0 to infinity. So the domain is it's all the possible x values because it is not possible to put a negative in here and still get a real number out. Okay. We'll look at some examples of this as well. Okay, which going along with domain is range. Range has a little bit more variation throughout it for certain graphs, especially if you see, so for instance, this function has the domain of everything, right? Now range, it also has everything because this goes on to infinity. And now remember, we're talking about the y values now. So it has all the y values. If you go up, this goes up to infinity and down to negative infinity. So this would have all possible values. But what happens now is for something like a parabola. Well, once you have a parabola, the y values below this are not included in the possible y values. If you're looking at this graph and there's no value at y equals negative 10. Okay, so it is limited that way. And we'll look at, like I said, in the examples we'll go through, and you're going to be given an equation and asked to find the domain and the range of that equation. Okay. You also have x-intercepts. Now, for an x-intercept, you can find it on your calculator, and I'm going to go through that in a second. But you can also, if you want to know where an x-intercept is, so for instance, if we have this little graph here, let's say we do have a, do like something like that. Well, if we want to know where it crosses on the x-axis, if you notice, the x-axis is where y equals 0. So if you set your function equal to 0 and solve for x, then that would give you any x-intercepts. You also, on your graph, on your calculator, you can graph this and do the trace function like we did in lesson 9. So you go through, you hit trace, and you type in x equals 0. And y equals 0. Oh, see, you know what, on the trace function, I think you can only type in x. So we can use that for finding our y-intercepts. For this, you have to go into the calculator, and there is a function that's called root or 0. So let's look at that for a second, and you can try that on, and we'll do an example with that. Okay, so pull out your calculator, and we're going to find the x-intercepts for f of x equals x squared minus 4. Okay, so this, when you graph it on your calculator, it looks like it is a parabola that is shifted down 4. So we want to find this value and this value. So in your calculator, I'm going to switch my color here so you can kind of see. We're going to go to, so after you graph it, so hopefully you're getting comfortable with that now, so you're going to go in, you're going to graph your function, and then if you go into second trace, so try this on your calculator right now, which is also the calculate function. So when I say second trace, that's how you get to it, is by pushing the button second and then the trace button, but this is the same thing as the calculate button, because if you see it in yellow there. So calculate is you find it by doing second trace. Now in there, mine is called 0. Depending on the calculator you have, it may be called, it could also be called a, I said it earlier, now it's like completely lost my mind. It's a root. So either a root or a 0. And mine, it's number 2, and it says 0. Like I said, I think my older calculator does say root. Okay, and it'll give you those same prompts that we did when finding the minimum and maximum. So it'll give you a left bound. So on there, you go to the left. It'll ask you for a right bound of where you're looking for. And, oops, I did mine. And then you ask it to guess. Okay, so then after I hit enter, it tells me that this is at -2, 0. And this one here, you do the same thing. You go back into calculate again, you find the 0, you do a left bound, you do a right bound, and you guess, and it tells me that this is at 2, 0. Okay, and this, when you're graphing it like this, you can see that there's 2 values. So for the same example, if I was going to use this example, this algebraic way of finding it, then we would let y equal 0. So then I would have 0 equals x squared minus 4. And then I would add 4 to both sides, so then I'd have x squared equals 4, because if I add 4, and I'm going to move my x to the left side because it makes me nuts if it's not, then we're going to square root both sides. So I have x equals the square root of 4. Well, what happens is when you take the square root of both sides, you do have to do plus or minus, and this is where you would get plus or minus 2, which is the square root of 4. So just showing you that that gives you the x values that where y equals 0. Okay, or you can find them with a calculator. Okay, so the y-intercepts, you can find it that same way by making your x equal to 0 and solve for y, or by looking at a graph. And it's mostly, so yeah, you're looking at for your x-intercepts, yeah, you're just looking anywhere where it crosses the x-axis, and then for your y-intercepts, it's where it's crossing the y-axis. Okay, let's go ahead and move forward. Okay, so hopefully these are things that you've kind of looked at before, that you've gone over before. Okay, so end behavior. Now, end behavior is looking at a graph, and graphs are predictable. When you're using graphs in algebra, you know what a graph is going to do. You see something that says x squared, and you know that it is a parabola. And depending on if there's negatives in certain places, you can tell if that's an upside down parabola or upside right parabola. Well, end behavior, we have to trust what's going to happen at the ends of things as you go to infinity or negative infinity. So for instance, on this graph here, I'm going to just draw you an example graph. Okay, let's say that I did have a function that looked like this. Okay, so here I'm going to call this graph f of x. Okay, so this is just my function that I drew. And I want to know what the end behavior is for this graph. Okay, so end behavior, I'm going to give you some notation and a way to write this algebraically. And this is something that we'll use in calculus as well. But we're going to talk about the limit. And I want to talk about the limit as x approaches negative infinity. So this is how we're going to write it, is the limit of f of x as x approaches negative infinity. Okay, so what this means is I want to know where is it going as x is going to negative infinity. Okay, so what happens is we look at this graph now and we think, okay, as x is going to negative infinity, what is happening to this graph? Well, as x goes to negative infinity, the y value is going to infinity. Okay, so we want to know as x goes to negative infinity, the y value goes to infinity. So the end behavior on that negative infinity side would be infinity. It would be going in a positive direction from this direction. So then let's look at what the end behavior is on the other side. So the way that we would write that, doing the other side, would be what is the limit of f of x as x approaches infinity? So now we're looking at the graph in terms of x going to infinity. And if you see here, this is going down, it has an arrow going down, and And because of the way that we graph things, we know that this will continue to go down. And so then this would have, this graph, what is happening in the y values is it's going to negative infinity as x goes to infinity. Okay, so let's look at another example. What about the graph just f of x equals x squared? Okay, well, we look at this and we can kind of be comfortable with this to know that this is a parabola that goes through 0, 0. Okay, so I have this, pretend like that goes through 0, 0, I have this parabola that goes through 0, 0. So if I'm looking now and I just want to know the end behavior, what is the limit as x approaches negative infinity of our function f of x? So looking at this, remember we're looking at where x is going to negative infinity, so x is going to negative infinity, and this graph is going to infinity. Okay, now what happens what's the limit of f of x as x approaches infinity? So now we're looking at it, and as it goes to infinity, this parabola is also going in a positive direction, in positive infinity. Okay, so the only time that there would really be a number there is if you had a horizontal line. And then that would be the end behavior, is it would be going to, if it had a horizontal line at 2, it would be going to 2. But most of the time, you're going to be giving either infinity or a negative infinity as to what the end behavior is. Okay, and then we're also going to look at, we want to know when it's continuous, and just a reminder that what are some things that make it not continuous. So if it has it has a denominator that can equal 0, then that would be somewhere where it is not continuous. If it has a negative under a radical. So we've decided that, you cannot take the square root of a negative number. I'm going to still kind of let that go over my work, sorry. And then also, like if a piecewise function doesn't connect, then that we've learned it gives us a situation where if it doesn't connect there, then that has a hole. So anywhere where there's a hole or something, then that creates a discontinuity. Okay, and then we also still want to look at where things are increasing and decreasing. Okay, the more we can know about a graph, the more that we can use that information. And getting comfortable doing this will really help us in calculus to find even more information from a graph about what's happening in real life situations. But first we've got to get comfortable with these simple examples, because real life is more messy than this. So these simple examples are kind of getting us into where you can do harder things. Okay, so let's look at an example where we're finding all of these things. And I'm going to try and move pretty quickly through this, but you're welcome to pause as you go so that you don't have to worry about writing everything down as I pull stuff up. So we're going to look at first, the first function I want to look at is 5x plus 2. So we're going to take, make sure I'm here, okay. So I have 5x plus 2. I'm sorry, I do want this to be, I'm going to call this f of x. 5x plus 2. So I want to know all of these things about this graph. I want to know, first of all, what the domain of this graph is. Okay, so what does 5x plus 2 look like? So as we get more comfortable with functions, I want you to be able to look at this and know that it is a linear function. The reason we know it's a linear function is because it only has an x of degree 1 in it and a y of degree 1, even though this is written in terms of f of x. And mostly when it's in this form, it's in the y equals mx plus b form, we can tell a lot more about it. We know that this crosses the y-intercept at 2, and it has a slope of 5, which means it goes up 5 and over 1. So 1, 2, 3, 4, 5, and over 1. Okay, so this is a super steep slope linear function. Okay, so what is the domain? Well, even though it's kind of narrow like this, because we have till infinity, as you get to x values, there is any x value you can plug in, you will get an answer back. So the domain is all real numbers. So sometimes you see domain, all real numbers written like that. It's like 2 lines and an R, but you can also write all real numbers if you'd like to write it out. So this is all real numbers. Okay, now what about the range? So we can plug in any x value and get a y out. Now can we plug in any y and get an x out? Yeah, absolutely. So a linear function has the domain and range of all real numbers. Okay, now what about the intercepts? So we do know that, and I just told you because of the form that it's in, when it crosses the y-axis right here, is at 2. So we know that it crosses at y equals 2. There's an intercept at y equals 2. And then if I want to know where it has an x-intercept, remember that we can either go onto our calculator and find it here, but it may be even faster just to go ahead and let y equals 0 and solve for x. So I'm going to go ahead and do that. So I'm going to say 0 equals 5x plus 2. And then I can subtract 2 from both sides. I get 5x equals negative 2. And that means that x equals negative 2/5. So we also have an intercept at x equals negative 2/5. Now what's nice about knowing a lot of this information is it makes it really easy to sketch the graph without a calculator. Because so far, right now, if we know it's a linear function and we know that it goes through 2 and it goes through negative 2/5, you can plot those 2 points and put the line through it and you automatically have a graph. Okay, what about end behavior? So what is the limit as x approaches negative infinity of f of x? Okay, so look at this graph that we've kind of sketched. As we go to negative infinity, this graph is going to negative infinity. So remember, this is when x goes to negative infinity. We want to know what happens to y. Y goes to negative infinity also. Okay, so what about the limit as x approaches infinity of f of x? Well, looking at the graph, we also can say, okay, well, as we go in the x direction to infinity, the y also goes to infinity. Okay, now what about continuity? So this is completely continuous, right? So it is continuous from, because there's no jumps, gaps, or holes in this linear function. So it's continuous from negative infinity to infinity. Now what about increasing and decreasing? So remember, you read a graph from left to right. So when we're going from left to right, is this going up or is it going down? So we look at from left from right and it is going up. So this is increasing from negative infinity to infinity. And there is nowhere on the graph that is decreasing. Okay, now it's important too that you answer all of these, even if there's not an answer, that you fill in none, so that I know that you know there's none and you just did not know how to do it, okay? You've got to make sure, especially when we test on this, that you do put everything in there. Okay, let's do one more example. Let's do a little bit harder one. I want to do f of x equals 8x to the negative 4/3 power. Okay, and remember all of the things that we want to find, and if you write down all of them at the beginning, it helps you not forget to do any of them. Okay, so let's start with domain. Okay, now this represents what would be, and I'll just do a quick review. We may have to do more on this in the future if people want more on this, but this bottom number is a root. Okay, so it is the root of the problem. Remember, the roots are down in the bottom. So this is the same thing as saying the third root of x to the 4th. And because it's positive, it's negative, it's really on the bottom. So this is what this is really like. It's like 8 over the cube root of x to the 4th. Okay, now a couple of things. One is that we are not actually that limited by this one, because there's very, as far as the radical, I should say, we're not really that limited, because a cube root is okay to be negative underneath, and you still have this number here that we're going to take to the 4th power, so it doesn't limit it as far as the root. But so now the only thing we have to worry about, because it is a fraction, is if the denominator were to equal 0. So the only way that the denominator could equal 0 is if there was a 0 in X. So the domain, so because we're looking at kind of our possibilities, is the denominator equaling 0, a negative under a radical, and I should say an even radical on this because it's got to be if it's an even number, or if it's a piecewise. Well, so right now the only thing that really limits us is that 0 in the denominator. So I'm going to go and say that this can go anywhere from negative infinity to 0 and from 0 to infinity. But right at 0, it has a hole there. You're unable, it's undefined right there at that point. Okay, now what about the range? Now when you're looking at the range, there really isn't that same stipulation that there's anything that's limited by what the y value could come out. Okay, so a way to look at, let's go ahead and look at the graph of this to just reaffirm that we agree that the range is all real numbers. So go into your calculator, go into your y equals, and go ahead and plug in. Now remember to put this negative 4/3 in parentheses. So you do 8 times x raised to the parentheses, negative 4/3 power, and graph it. Okay, so what happens is that there is this asymptote at 0. And this, so I'm so glad we graphed it because I am seeing a stipulation on this range. So because of the way that these follow this asymptote at 0, and it's following this, a way you can kind of test this on the graph is go ahead and trace and try and get anywhere where you think it would be a negative value in y. And you can't, as you're tracing, you can kind of see what's happening to the graph. But yeah, it doesn't. There's no way to get a negative number out of this. Now the reason is, and I should have thought of this too before, but you're taking x and you're squaring it. You're taking it to the 4th power. So no matter, even if you put a positive or negative value in there, it's always going to be positive. Okay, so the range is really only from 0. And we're going to go ahead and include 0. And actually, no, we can't even include 0 because there's no way for this to equal 0 because there would never be a 0 on the bottom. So this is actually going to be a soft bracket like this. 0 to infinity would be the only possible y values in that graph. Okay, what about x-intercepts and y-intercepts? So when we look at this graph, they're approaching these axes, but they're actually never approaching them. So there are no intercepts. X and y, there's no intercepts. Okay, now what about end behavior? So let's remember, practice our notation here. The limit as x approaches negative infinity of our function f of x. What's happening to our graph as x goes to negative infinity? Well, this, if you see, is approaching 0, but it's never crossing over, right? So we have this asymptote here also, and it's approaching this. When you trace on your graph, you can kind of see it's never going. Now, this is where graphs are predictable. You kind of have to trust. When you see a graph shaped like this and there's asymptotes involved, this, as you get closer and closer, will get close, but never get to negative infinity. Never get to 0. It'll just get closer and closer to 0. So let's do. Okay, so I'm going to take and say that this has an end behavior of 0. It's going to 0. And the limit as x approaches infinity of f of x has the same problem, right? It is also going to 0. So I'm going to take back kind of what I said. So I didn't account for horizontal asymptotes when I was talking about those limits before. So a horizontal asymptote is also going to be an option as opposed to just a horizontal line. If there's a horizontal asymptote, then it'll also go to a number instead of infinity. All right, so now let's look at where it's continuous. Now this graph is not continuous at 0, right? But everywhere else you can kind of draw the line. So this is continuous from negative infinity to 0, from 0 to infinity, And now increasing. So the graph, remember we're reading from left to right. It is going up from negative infinity to 0. And then where is it decreasing? Well, it's decreasing from 0 to infinity. And that is, we're getting all that information about each of those graphs.